Hello everybody and welcome back. We're going to continue our look at the 2013 Friar Contest. We're up to question number 3 now. So let's grab our pens and we'll take a look at the question. Alright, so number 3. The sum of the digits of 2013 is 2 plus 0 plus 1 plus 3 equals 6. 2 plus 0 plus 1 plus 3, 6. If the sum of the digits of a positive integer is divisible by 3, then the number is divisible by 3. Also, if a positive integer is divisible by 3, then the sum of its digits is divisible by 3. Okay. So, you're divisible by 3 if and only if the sum of your digits is divisible by 3. This is a divisibility rule. Okay? It's something that you hopefully have seen by now, but if not, okay, they're introducing it to you. That's great. So I have 4 parts in this question, and I'm betting that sum of digits is involved somewhere. So A part, list all values for the digit A such that the 4-digit number 51A3 is divisible by 3. Alright, so we just need our final answer here. Now, A is not a leading digit, so that means A could be 0. That's entirely possible. Now, 3 divides 51A3. Well, that implies that 3 divides 5 plus 1 plus A plus 3. Or really 3 divides 8 plus A. Oh, sorry, 9 plus A. Do I have these numbers right? Yeah. Okay. Always got to double check, otherwise you're not solving the question they asked for and you get 0 marks. So 9 plus A. Okay. So we could do a couple things. We could realize, well, 3 divides 9. So in order to divide 9 plus A, 3 has to divide A. That's certainly one way to do it. Another way to do it is to say, okay, we need all multiples of 3 in whatever range 9 plus A can be. Well, can be between 0 and 9. So that means 9 plus A, between 9 and 18. So A plus 9 can be 9, it can be 12, it can be 15, or it can be 18. All multiples of 3 in this range. And so we get A is 0, 3, 6, or 9. And those are the possible values that A can be. Alright, so that's A part. B. List all values for the digit B such that the 4-digit number 742B is divisible by both 2 and 3. That is divisible by 6. If you're divisible by a compound number, you break it into its prime factorization, and you just need to be divisible by each of the prime factors, the prime powers that make up your number. So 6 is 2 to the 1 times 3 to the 1, so in order for this number to be divisible by 6, it's got to be divisible by 2 to the 1 and 3 to the 1. Okay. So, 4-digit number here, well, we know how to get divisibility by 3. They give it to us. We need to have a sum of the digits be a multiple of 3. To be divisible by 2, the last digit, the units digit, has to be divisible by 2. Okay? So that narrows down our choices for B. So 742B, I believe, but let's just double check that. 742B. Okay. Well, that tells us that 3 divides 7 plus 4 plus 2 plus B. Well, if we group that all together, we have 7 divides, that's 11, so 13 plus b. So once again, b is not a leading digit, so it can really be whatever we want, 0 to 9. And that means that 13 is less than or equal to b plus 13, less than or equal to 9 plus 13, so that's 22. B plus 13, the b's kind of look like 13s, and I do apologize for that. I'll connect my b's a little more. So b plus 13, it's got to be a multiple of 3. Okay? It's got to be a multiple of 3. Well, what multiples of 3 do we have in this range? We have 15, we have 18, and we have 21. That means b is 2, or 5, or 8. So we just subtract 13 off of each of these, and that gives us possible values of b. So if you want to be divisible by a power of 2, your last so many digits have to be divisible by that power of 2. So if you want to be divisible by 2, so that means the last digit must be even. Well, b is the last digit. Can't be 5. It can only be 2 or 8. So b could be 2 or 8, and those are the only possible values. And if we wanted to, we could double check that 7, 4, 2, 8 is divisible by 6. Yeah, it's 1,238 times 6. So that's B part. Those are 2 light bulb questions. They just asked us to list out values of A and B. But we did a bit more explanation than we needed. Alright, so C and D are the written portions. Find all possible pairs of digits, P and Q, such that the number 1, 2, 3, 4, PQ, PQ is divisible by 15. Okay. So to be divisible by 15, you need to be divisible by 3 and 5. Okay. Divisible by 15, you're going to have divisibility by 3 and 5. Well, we know divisibility by 3. We've been doing that the whole question. So, we want 3 to divide 1, 2, 3, 4, PQ, PQ. Then 3 divides, we'll skip a step and we'll just say it's 10 plus 2P plus 2Q. Okay? Now, are we asked for values, possible pairs of digits P and Q? Okay. So we do want to work out P and Q. Sometimes they ask us to do something special, like just determine what possible values P plus Q can be. Alright. So 3 divides 2 times 5 plus P plus Q is one way to write this. Okay. Well, 3 being a prime number, either 3 divide, if you have a product, if you have a prime, divides AB, then either P divides A or P divides B. This is a rule of primes. In fact, in some cases, it's very akin to the definition of a prime. I think in ring theory, you have this condition and a couple other things. But we're getting ahead of ourselves. This is just 9th grade. This is the basic prime number fact that you should know. So we have a product here. 3 divides 2 times 5 plus P plus Q. 3 doesn't divide 2. So 3 divides 5 plus P plus Q. Okay. So that's something we can note. And we could probably get values for P and Q here. But we're going to have a lot of potential values for P and Q, and I don't want to deal with those right now. So let's switch to divisibility by 5, and maybe we'll get another fact that we can combine it with this, and we might simplify things. So just like divisibility by 2, if you want to be divisible by 5, then your last, if you're divisible by 5 to the power of k, your last k digits must be divisible by 5 to the k. So if we're just divisible by 5 to the power of 1, it means your last digit, your final digit, must be a multiple of 5. So your last digit can be either 0 or 5. So Q is 0 or 5. Well, that's actually really nice. It's almost, we probably should have started with that one. So now we have two cases. If Q is 0, which it's entirely possible that it is, then 3 divides 5 plus P plus Q is 3 divides 5 plus P plus 0. 3 divides 5 plus P. Once again, P is not a leading digit, so it can be anywhere between 0 and 9. So P plus 5, which we want to be divisible by 3, is between 5 and 14. So P plus 5, it can be 6 or 9. We're just looking for the multiples of 3, so 12. And that means P is 1, 4, or 7. So PQ can be 1, 0, 4, 0, or 7, 0. And we could double check. 1, 2, 3, 4, 7, 0, 7, 0. Is that divisible by 15? It absolutely is. Okay. So that's one way of doing this. But the other case is Q equal 5. And 3 divides P plus Q is 3 divides 5 plus P plus Q is 3 divides 5 plus P plus 5, or 3 divides 10 plus P. Well, 0 is less than 9, less than P is less than 9. That means 10 is less than P plus 10 is less than 19. And we're looking for multiples of 3 here. So multiples of 3 from the range 10 to 19 inclusive. So P plus 10, it could be 12, it could be 15, or it could be 18. And that means that P is 2, 5, or 8. So PQ could be, well, we had the ones from the previous page. And now the ones here, 2 and Q is 5. once again, we could probably pick one of these, like 1, 2, 3, 4, 2, 5, 2, 5, and see if that's divisible by 15, and indeed it is. So those are our only possible values for P and Q. And we used our divisibility rules. We stated the divisibility rule for 5 because that wasn't given to us in the question. We got into 2 cases to look at. And then we were able to get ourselves a final answer. So 6 possible values there. So we have all possible pairs of digits. Okay. So now we have D. Determine the number of pairs of digits, C and D, for which the product 2cc times 3d5 is divisible by 12. Okay, that's another written style question. So, if we want to be divisible by 12, well, what have we been saying? If you want to be divisible by a composite number, so a number that isn't prime, you prime factor it, and then you have to be divisible by each of the prime powers there. So 12 is 2 squared times 3 to the 1. So you're going to have to be divisible by 4 and by 3. Now, we have a divisibility rule for 3. And I hinted at divisibility rule for 4 back in part B. Okay. So we'll just write it out now. So we have 2 to any exponent, really. Okay. So really, this works for any power of 2. But to be divisible by 4, the last 2 digits must be divisible by 4. If we were divisible by 8, which is 2 to the 3, then the last 3 digits would have to be divisible by 8. If we were divisible by 32, the last 5 digits would need to be divisible by 32. So this is general power of 2 divisibility rule. And we know how to be divisible by 3. Okay. And we want 12 to divide 2cc 3d5. Okay. So we need to have 3 divide that, and we need to have 4 divide this. Fantastic. Okay. Well, here we have a prime number, 3, and a product. So we could have 3 divide 2cc, or 3 divide 3d5, or it could happen to divide both of them. But we will have 3 divides at least one of them. Okay, so there's not really a plan of attack there. There's just sort of 3 cases. Is it divisible? Is 2cc divisible by 3? Is 3d5 divisible by 3? Or are they both divisible by 3? Either or. How about divisibility by 4? Okay. Well, if we want a divisibility by 4, one thing that jumps out to us is 3d5 is odd. So neither 2 nor 4 divide 3d5. And that means that 4 will have to divide 2cc. Because normally we could either have 4 divide the first number and don't really care what happens to the second number. We could have 2 divide the first number, 2 divides the second number, or we could have 4 divides the last number and no one cares about the first number. But since our second number is odd, those last 2 scenarios can't happen, so 4 must be a factor of 2cc. So 2cc must be divisible by 4. And what is our divisibility rule for 4? Well, the last 2 digits have to be a multiple of 4. So cc, which is c times 11, is going to be a multiple of 4. Now, 2 and 4, they don't divide 11. So that means that 4 divides c. So c can be 0, it can be 4, or it can be 8. Okay? We have these possibilities. Because c is not a leading digit, so it can be 0. Okay? If c is 0, well, the multiple of 4 is already accounted for. We need 3 divided 200 times 3d5. But 3 is not a factor of 200. So 3 divides 3d5. And what do we know? Well, we know that the sum of the digits of 3d5 will then have to be a multiple of 3. So we get 8 plus d. So d plus 8 is going to be in the range 8 to 17. So d plus 8 can be 9, it can be 12, or it can be 15. We'll make that actually look like a plus sign. And that tells us that d is going to be 1, 4, or 7. So we could have CD is going to be 0, 1, 0, 4, or 0, 7. And that's just this case. Okay? And if we wanted to, we could double check. We could say 200 times 315. Well, that's 63,000. Is that a multiple of 12? It absolutely is. All right. We have another case. If C is equal to 4, we have 2, 4, 4, 3d5. Well, 2, 4, 4, is that a multiple of 3 already? No. So, since 3 is prime, and it divides, we know it divides this product, and it doesn't divide this factor, it's got to divide this factor. But we already know what it looks like when 3 divides 3d5. We know that d ends up being 1, 4, or 7. So we have 4, 1, 4, 4, and 4, 7. Okay, we get 3 more cases. Fantastic. Now, if we have 2, 8, 8, and 3 doesn't divide that, we'll get the same values of d again. We'll get a total of 9 values. So our last case, if c equals 8. Well, we're looking at 3 divides 288 times 3d5. But 3 divides 288. Specifically, 96 times 3 is equal to 288. So no matter what value of d we have, we know that it's already, this product, 288 times 3d5, is already divisible by 12. So d can be any value from 1 to 9. It really doesn't matter. Pick one at random. Let's say 7. 375 times 288 is 108,000. Is that divisible by 12? You bet it. That's 9,000 times 12. So therefore, in total, CD could be 0, 1, 0, 4, 0, 7, 4, 1, 4, 4, 4, 7, or 8, 0, 8, 1, 8, 2, 8, 3, 8, 4, 8, 5, 8, 6, 8, 7, 8, 8, or 8, 9. And those are all the possible values, and I think that's all we were asked for. Oh, determine the number of pairs of digits. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 pairs. Alright, so we double check, we carefully read the question, because they want the number of pairs, they don't actually care about what C and D are. So we get a total of 16 pairs C and D. Alright, so that concludes question number 3 on the 2013 Fryer contest. We just have one more question to go, and that's question number 4. So hopefully you'll join me in the next video as we take a look at the last question on the 2013